Back to life, back to reality, section 3.1. This is lesson 8 in SUNY Genesio's Math 221 Calculus 1. We start to talk about a really big, serious, important calculus word, the idea of a derivative. This is where we park ourselves for the next few weeks in our course together. We talked at some length in class about the idea of here's a function and there's some place where we're interested in finding the slope of a tangent line. Here's the value f of a. And so we can't find the slope of a tangent line because slope requires 2 points and tangent lines only touch at 1 point in a small neighborhood. And so we picked this other point, this other movable point x. Here's f of x, and we found the slope of the secant line through those points. How did we do that? Well, we figured out some number q, and that number is change in y over change in x. There are other mathematicians who look at the question slightly differently. They say, all right, here's my function, and here's my point of interest. And then let's scooch over just a little bit. We're just going to move over by some tiny little bit. We're going to call that h, so that this number here is a plus h. And so this is the other point of interest. This is f at a plus h. And they also draw a secant line, and they pretend that the secant line is like the tangent line. And we again find the slope. We'll call that slope q because it's the same kind of slope, so I don't have to change names from this one. And again, the slope of the line is the change in y over the change in x, but the change in x is just h. Excuse me. In both cases, we call q a difference quotient. And all that means is it's a quotient of differences. It is a slope of a secant line. We find the slope of a secant line. We pretend that it is the slope of a tangent line. To find the slope of the tangent line, we take this point and we slide it along the curve until it is so close to that one. We take this point and we slide it along the curve until it is so close to that one that you can hardly tell the two apart. And that is exactly what we've been talking about. It's this idea of a limit. And so to get the slope of a tangent line, we actually take a limit. And this is screenshotted right out of page 225 of your text. The slope of a tangent line is given by taking this difference quotient and pushing x toward a. Taking this difference quotient and pushing x toward 0. The effect is the same. To push x toward a is to push h toward 0. So you have got to be comfortable with either of these definitions. This is the blue way. This is the red way. You've got to be comfortable with both of those. For example, find the equation of the tangent to y equals x squared. Oh, let's not call it y. Let's call it f of x, just to be safe, at a equals 2. So how do I find the equation of a tangent line? Well, I remember how to find the equation of a tangent line. That's y minus y1 equals x minus x1 multiplied by the slope. And that's where the formula comes from. So this is the x value, so the y value is 4, and then all we need is a slope. Well, how are we going to find the slope? Well, the slope of a tangent line is the limit as x approaches 2, this 2, of f of x minus f of a over x minus a. And so you say to yourself, well, that's easy. I'll just plug in 2 and be done. Go ahead, plug in 2. I'll wait. Oh, yeah. See, that's 0 over 0. That's not something we can work with. So we try factoring. And then, well, looky here. So that's the limit as x approaches 2 of x plus 2, and sub that right in there. 2 plus 2 is 4. Slope of the tangent line is 4. That's a 4. That's the equation of your tangent line. You can leave it in point slope form. That's fine. You can get in y equals mx plus b form. That's fine. Does not matter. Find an equation of the tangent to g of x equals 1 over x at a equals 3. How do I find the equation of a tangent line? I know how to find the equation of a tangent line. It's y minus y1 equals x minus x1 multiplied by the slope. And that's where the formula comes from. The y value is easy enough. If x is 3, the function value is 1 over 3. The question is, what is this slope? And so we ask ourselves what the slope of the tangent is. Here I'll use the other definition. It is not that one definition is easier sometimes and the other is easier sometimes. I just want to show us how to work with both. I'm going to take the limit as h approaches 0 of the function at a plus h minus the function at a over h. Well, I'll just plug in 0 and be done, except that, well, we're not. So what happens now? Well, here we go into scrapland, and over in scrapland, we figure out how to subtract fractions with different denominators, and this isn't terribly awful. We find ourselves a least common denominator, and that's just the product of the two denominators. So this needs a 3, and this needs a 3 plus h. And so this is 3 minus 3 plus h, and this turns out to be negative h. And so you still have the problem, you can't throw the 0 in because those are both 0, but the funniest thing happens, and the thing that happens is that these cancel, and so you end up with negative 1 over 3 times 3 plus h, and then we ask, well, what happens as h goes to 0? As h goes to 0, this numerator is unaffected, and the denominator is 3 times 3, that's 9. And that's the slope of the tangent line. And that's how it goes on your paper. You can leave it in point slope form. You can put it in y equals mx plus b form. It does not matter at all. You should try yourself. You should try find an equation of the tangent to h of x is radical x at a equals 1. So, curious thing. This m tan thing that we keep doing, this m tan thing, the slope of a tangent, this m tan is what we in calculus land refer to as a derivative. And the process of finding it is the process we call differentiation. And your author offers the following. So again, it's the same setup. You have some function, it's defined in some interval that contains a, the derivative of the function. And the derivative is denoted by f prime. That's red f prime. It's an apostrophe if you're using Microsoft Word or LaTeX. F prime of a. So f prime of a, this is the blue definition from a couple of slides back. F prime of a is the limit as x approaches a of a difference quotient. F prime of a is the limit as h approaches 0 of a difference quotient. When we talk about f prime of a, we are talking about the slope of a tangent line. When we're talking about the slope of a tangent line, we are talking about f prime of a. One more example. Estimate and then find f prime of 3 if f of x is x squared minus 2x minus 3. Estimate and then find f prime of 3 if f of x is x squared minus 2x minus 3. So what we could do on the estimating front is we could pick some numbers that are really, really close to 3. I mean, we're looking to see what happens at x equals 3. We could pick some numbers that are really, really close to 3, and then we could figure out the difference quotient, f of x minus f of 3 over x minus 3. We could figure out what those are, and if we pick numbers that are closer and closer to 3, we could see what the slopes are getting closer and closer to. So I did that with some numbers that are close to 3 on the left-hand side, and I got answers that looked astonishingly close to 4. And then just in case you thought that it might be different the other way because of that thing we did in class, and you're wise to remember that, I got answers that were astonishingly close to 4. So it is a decent guess that f prime of 3 is 4. That's an astonishingly good guess. We can prove that. We can prove that f prime of 3 is 4. How? Well, it's the limit as x approaches 3 of f of x minus f of 3. Well, what's f of 3? 9 minus 6 minus 3, 0 over x minus 3. And you're saying, I'll just throw the 0 over 0. You knew that was coming. So the numerator factors, go figure. Of course it does. And these drop out. And so what is that? Well, the 3 goes in here. 3 plus 1 is 4. And that confirms that f prime of 3 is 4. The slope of the tangent line to this curve at x equals 3 is 4. Excellent. So we will see each other in class. There will be some things we should talk about. And then I have a quick thing about some applications of this concept. Thanks for hanging for 14 minutes. We'll see you in class.